Hey there, as someone who's spent years in the trenches as an industrial cybersecurity architect, I can tell you that defending our critical infrastructure is one of the biggest challenges out there. So today, we're going to dive into one of our most powerful tools for the job, IEC 62443-3-3. Think of it as the master blueprint for building secure operational technology systems, especially for something as vital as our energy grid. You know, this is the kind of question that keeps us architects up at night. And believe me, the answer isn't some magical silver bullet you can just buy and install. It's actually something much more fundamental. It all starts with the system's architecture, with designing security right into the foundation, instead of trying to patch it on later. So here's our game plan for today. First, we'll look at the big problem we're trying to solve. Then, we'll walk through how to build a risk-based solution step by step. After that, we'll get into the specific technical controls you'd use, and finally, we'll see how it all pulls together to protect something like the power grid. Sound good? Let's jump in.
Okay, so first things first, let's really understand the problem that this standard was created to solve. A lot of older industrial networks are what we call flat. That means everything can talk to everything else. Imagine a house with no internal walls. In today's world, that's just a recipe for disaster. It means one compromised laptop could potentially take down an entire plant. Now, it's important to know that IEC 62443 isn't just one document. It's a whole family of standards. There are parts for general concepts, policies, and even for individual components. But we're focusing on Part 3.3, which is right in the sweet spot for us architects. It's all about system security. It's the playbook for designing a tough, resilient system from the ground up. All right, let's open up the Architect's Toolkit. The entire philosophy behind 62434 hinges on one absolutely critical idea. Your security design has to be driven by risk. What does that mean? It means you don't just sprinkle security controls around like fairy dust. You figure out what's most important, what the threats are, and you focus your defenses there. It's about being smart, not just busy. And this quote right here, this is rule number 1. Before you can even think about designing a defense, you have to know exactly what you're defending. You can't protect a ghost. So every single secure design process kicks off with a detailed risk assessment of the entire control system. Seriously, this step is completely non-negotiable. So what does this risk assessment actually look like? Well, it's a very methodical process. You start by making a list of everything you have, every controller, every workstation. Then you brainstorm all the bad things that could happen, the threats, and look for weaknesses. And here's the key part that separates OT from IT. You have to figure out the physical impact. We're not just talking about data loss, we're talking about safety. From all that, we can finally create a prioritized list of what we absolutely must protect. Okay, once we know our risks, we can finally start to design. And our first major tool is the concept of a zone. Just think of it like building a medieval castle. You wouldn't just have one giant wall around everything. No way! You'd have secure rooms inside, right? The treasury would be way more protected than the stables. That's exactly what a zone is, a grouping of assets that need the same level of protection. So if the zones are your secure rooms in the castle, how do you get between them? That's where conduits come in. A conduit is simply the guarded hallway or the locked door that connects your zones. By defining these pathways, we can put a guard, like a firewall, in charge and strictly control who and what gets to pass from one area to another. This is the very essence of network segmentation. So let's make this feel a bit more real. If we were designing for a power grid, what would our zones look like? Well, for starters, you'd put a massive wall between the corporate IT network and the control systems. The main SCADA control center, that's its own high-security zone. Each electrical substation could be a zone, and all the little devices out in the field could be another. By chopping the network up like this, you contain any potential breach, stopping it from spreading like wildfire. Now, not all zones need a fire-breathing dragon guarding them, right? This is where security levels come in. They let us quantify how strong the defenses for each zone need to be. SL1 is basically for oops moments, protecting against accidents. SL2 is for your casual hacker. SL3 is for serious professional attackers. And SL4, that's when you're worried about spies and nation-states. Our risk assessment tells us exactly what the target security level, or SLT, needs to be for every single zone. Okay, let's do a quick recap. We've drawn our map, we have our secure rooms, the zones, we have our guarded hallways, the conduits, and we know how strong the walls and doors need to be for each one, our security levels. Now, and only now, can we start talking about the actual bricks and mortar, the technical controls like firewalls and authentication that will make it all real.
Now, you might be looking at this list and thinking, wow, there must be hundreds of possible security controls. And you'd be right. But the standard does something brilliant. It groups them all into these 7 main buckets called foundational requirements. This framework makes sure we cover all our bases, from who can log in, to protecting our data, to making sure the system stays up and running.
Let's zoom in on a couple of these because they are so critical in the OT world. System integrity. This is all about trust. How do you know that the code running on a critical controller is the real, authorized code from the manufacturer? A great example of a control here is using digitally signed firmware. It's like a digital wax seal that proves the code hasn't been tampered with by an attacker. And what about restricted data flow? Well, remember our conduits, the guarded hallways? This is the guard. This is how we enforce the rules. We can place a firewall on that conduit and give it a very strict list of instructions. It might say, only let this specific type of traffic from this one server talk to this one device and block absolutely everything else. This is how we bring our architectural drawing to life. So, you see how we've moved from the big picture concepts all the way down to the nitty-gritty technical details? Let's pull the camera back out now and see how this all comes together to protect something as massive and critical as the power grid. And, just as important, how we keep it safe day after day. And what do you know? When you look at the widely accepted best practices for cybersecurity in the energy sector, you start to see 62443 principles everywhere. Strict IT/OT segmentation, that's just a fancy way of saying zones. Secure substation communication, hello, conduits. Every one of these is a real-world application of the risk-based, segmented design we've been talking about. It's also super important to see how this fits with regulations. Think of it this way. A regulation like NERC-CIP in North America basically says you must build a secure system. It tells you what to do. IEC 62443 is the detailed engineering guide that shows you how to do it. It's the building code that helps you actually meet the law and, more importantly, be genuinely secure. Now, if there is one thing I really want you to take away today, it's this. You cannot just design a secure system, turn it on, and walk away. It doesn't work like that. A great design is the starting line, not the finish line. Threats change. New vulnerabilities pop up, and your system has to evolve with them. Security has to be a living, breathing process. So, how do you make security a continuous thing? Well, it all comes down to visibility. You have to be watching your network. You need tools that can spot when something just doesn't look right. We call that anomaly detection. And all of that information needs to be collected and analyzed so that you can spot the bad guys early before they can cause any real damage. All right, let's boil this all down. If you remember just 4 things from this explainer, make it these. 1. 62443-333 is your blueprint for secure system architecture. 2. Everything, and I mean everything, has to start with risk. 3. Zones and conduits are your best friends for stopping an attack from spreading. And 4. Security levels give you a clear target for how strong your defenses really need to be. So today, we focused entirely on designing the secure system, the secure house, if you will. But of course, that house is built out of individual bricks, windows, and doors. The next part of the standard, the 62443-4 series, is all about making sure those individual components are built securely from the very beginning. And that's the final thought I want to leave you with. It's easy to get caught up in regulations and checklists, but the real goal here isn't just to check a box and make an auditor happy. The goal is to build systems that are truly resilient, systems that can actually take a punch from a real-world attacker and keep on running. That's what really matters. Thanks for your time.